So, in module number 5, we will take a look at a simple value stream mapping example, and we will draw a current state map to understand how the value stream map is constructed and what type of information is available. Then in the next session, the next lecture, we will understand how that particular current state map is analyzed from using lean principles, so that we are able to improve that current state map so that it moves towards the goal of lean. So in our example, we will talk about a company which, for want of any creative name, we call ABC Incorporated. And this particular company makes a particular part from sheet metal. We will assume that this part is produced in two varieties, a left side and a right side. A lot of times parts, and this could be an assembly also, the parts used in a vehicle tend to be, one for the right side and one for the left side. So it could be, two different types of parts, or it could be two parts that are used on two different sides of a finished good. The historical demand for this particular product has been, on a monthly basis, 12,000 of the left side part and 6,400 for the right side part. You're given information that the plant works 2 shifts and the parts are packed in trays of 20 parts each. So there's some sort of trays in which 20 parts are packed, and 10 trays are packed on each pallet, which are then shipped to the customer, and there's 1 shipment per day to the customer. As far as the manufacturing steps are concerned, we have 6 manufacturing processes. We have a stamping or a blanking press. We have a spot welding station 1. We have a second spot welding station. And the reason why we have depicted both of them is because these are used in series, and there is inventory that accumulates between them. Then we have 2 assembly stations, and these are again depicted as separate processes because we do not have this as a continuous assembly process using some kind of a conveyor, but there is a inventory that accumulates between the 2 assembly stations. And the last step is a shipping step or a shipping process. Some information with regard to the rate of demand. The total demand rate, which includes both the left side and the right side part, is we had 12,000 for, I think, the left side and 6,400 for the right, or the other way around, but the total came to 18,400 pieces per month. Now, if we assume 20 working days in a month, okay, assuming a 2-day work week, a 2-day weekend, that means a 5-day work week and 4 weeks in a month. So if we assume 20 days, if you have a 25-day work week or a 26-day work week or a 24-day work week, you can use whatever numbers you actually need. But here we have tried to keep things a little bit simple, and so using 20 work days a month, this translates to 920 pieces per day. Now, the time available per shift. Okay, now typical time in an 8-hour shift is 480 minutes, but here we will assume that in that 8-hour shift you provide for 2 10-minute breaks for tea, one in the morning maybe and one in the afternoon or evening, and so the total time that is available per shift for production is 460 minutes multiplied by 60 seconds, for a total of 27,600 seconds. Now you might ask, why do we calculate time in seconds? The reason why we calculate time in seconds is because we're going to use this for the purposes of calculating the takt time, and the takt time is generally stated in seconds. So we now calculate the takt time. Remember, the takt time represents the demand rate from the customer. So we have 27,600 seconds available for production in a day. Now in that 27,600 seconds, the total pieces that the customer demands is 460. Why is it 460? Because the total demand we said was 920 pieces per day, but we work 2 shifts. So per shift the demand is going to be 460 pieces. So therefore the takt time, which is the amount of time that would elapse between 2 pieces in terms of the rate at which the customer demands the product, is 27,600 divided by 460, or it is 60 seconds. So therefore what that tells me is that one finished part must happen, or one part must be completed every 60 seconds to keep pace with the rate of customer demand. If our rate of production is slower than that, we will not meet the customer demand. If our rate of production is faster than that, we will generate inventory, and both of those are undesirable. Now we will walk through the process, and what we need to observe is the amount of inventory that is there on the shop floor. And let's say that what we observe is there is coil stock, which is the first part that is required. This is the raw material that is arriving from the supplier, and there are 5 days of coil stock. There is no point in talking in terms of pieces of inventory here, because a coil is a single coil, and it is very difficult to measure how many pieces would be in a single coil. So we measure it in terms of number of days of stock, of coil stock. Then we take a look at the first process, which is stamping or blanking, and the next process, which is spot welding station number 1, and we observe that there are 7,000 pieces between these 2 processes. Okay, this is information that is given. Okay, and the inventory in pieces between the first and the second spot welding processes is 1,700 pieces. The inventory between the second spot welding process and the first assembly station is 2,450 pieces, and the inventory between the first and the second assembly station is 1,840 pieces, and the inventory between the second assembly station and shipping or dispatch is 4,140 pieces. So now we are going to depict all this information graphically. Now the way in which we depict it, first of all, we have a supplier. The supplier gets information in terms of a weekly plan from a central PPC. So this is where the information is also being mapped, and the information is going from this centralized PPC. And sometimes what we tend to do is, if we have a computerized plan, we can sometimes show this with the help of a sort of squiggly line. A paper schedule or a paper plan is depicted with a straight line. Okay, so the supplier receives the information. Let's say this is with the help of a fax or paper schedule, and then the supplier supplies the coils that are shipped twice a week. And the 6 steps that we have are stamping or blanking, welding station 1, welding station 2, assembly station 1, assembly station 2, and shipping or dispatch. Okay, and so this is the sequence in which the material flows through the plant, and then from dispatch the finished product is dispatched to the customer once a day. Okay, and the customer will provide his or her input in terms of demand or requirement to the PPC. Okay, so that if it is through again electronic means, then it will be shown with a squiggly line, but if it is with the help of fax or paper form, then that is sent, or that is depicted with a straight line. So that's the basic process. Now we'll start to add some detail in there. So the current state map, as we walk through the process, we start to indicate the fact that we have a supplier, and the supplier dispatches through a truck twice a week coils, and these coils are sitting in inventory before the first step, which is the blanking step. And this inventory, we have noted, is 5 days of coil stock. Okay, the first stage in our process is a blanking stage, and the data block or data square below the blanking indicates things such as the cycle time, which is 1 second. It's a very fast process. The changeover time is 1 hour. Let's say uptime is 85%. You could also indicate other information such as percentage defective, number of operators, and number of shifts worked, etc. Then, first of all, you notice the type of arrow which indicates movement of material between the blanking and the first welding station, and this type of a broken arrow indicates that this happens as a result of push. That means each one of these individual stations receives its own independent schedule, and as each one of these processes finishes the material that it has received, it will just transfer it to the next station irrespective of any signal coming from the next station, and that is what we call a push method. And there is inventory between the blanking and the welding station. The total inventory is 7,000 parts, and this is broken down into 4,600 left and 2,400 right, but the total number of pieces in inventory is 7,000. This is given to us. The information between the first welding station itself has a cycle time of 39 seconds, a changeover time of 10 minutes, and an uptime of 100%. And the inventory between the first and the second welding station is a total of 1,700 pieces, of which 1,100 are left and 600 are right. And the information corresponding to the second welding station is given over here. That is a cycle time of 46 seconds, changeover time of 10 minutes, and an uptime of 80%. This is only half the current state map because I've used 2 slides to actually complete the entire VSM, the current state map. Now, from the second welding station, between the second welding station and the first assembly station, there is a total of 2,450 pieces in inventory, and the particulars of the first assembly station are that it takes 62 seconds to complete this assembly task. There is no changeover time, and it's 100% uptime. The inventory between the 2 assembly stations is given over here, which is 1,840, and the cycle time for the second assembly station and the uptime is given over here, and the inventory between the second assembly station and the dispatch is 4,140, and then you are told that the dispatch to the customer is once a day, and the customer demand is 12,000 left and 6,400 right. Now, this is part of the current state map. There's one more piece of information that we're going to add, which is a very important part of the current state map, which is going to be done right here. We draw at the bottom of the current state map a sort of a broken line, if you will. It's not a continuous line. It is at 2 levels, and what you record here is the amount of time depending on whether this line is below a value adding step or a non-value adding step. A non-value adding step is typically inventory. Okay, so when you see inventory, below that you will have in days the total amount of inventory. So we convert the inventory, if it is in pieces, into number of days of inventory. Now, coil stock is already in terms of number of days of coil stock, so therefore we have 5 days of coil stock. This next information is about the time that it takes to do this value adding step, because the next thing that happens to this particular part is a value adding step, that is the blanking process, and the cycle time for this particular process is the value added time, and so that is entered just above this particular line over here. Now, the next thing that happens here is that part sits in inventory and there are 7,000 pieces. Now how do we convert 7,000 pieces into 7.6 days? Well, we divide this total inventory by the demand rate. The demand rate is 920 pieces per day. So if I were to divide 7,000 by 920, I will get the total number of inventories or the total days of inventory that these 7,000 pieces represent. Note that the inventory in days is not going to be calculated based on either the rate of production of the blanking press or the rate of production at the welding station. It is in terms of the customer demand. Okay, the rate of customer demand is what determines the number of days of inventory. So we have 7.6 days of inventory over here. The value added time in the first welding station is the cycle time, which is 39 seconds. The 1700 pieces of inventory between the two welding station amounts to 1.8 days of inventory. The value added time is 46 seconds at the second welding station. The total inventory between the second welding station and the first assembly station is 2450, and this calculates to 2.7 days of inventory, and the value added time at the first assembly station is 62 seconds. Similarly, the inventory between the two assembly stations is 2 days because this is a total of 1840, and the value added time at the second assembly station is 40 seconds, and the inventory between the second assembly station and dispatch is 1.5 days. Now if you add together the total amount of time in the non-value added stages and you list it here, and you add all the value added time and you list it down here, this is where you get a real impact in terms of how much of the total time that the part spends in the system does it actually spend in value added activities. So what you see is that the total value adding activities amount to just about 3 minutes. It's 188 seconds. However, that part spends close to 24 days to complete all of these processes, which should be completed in about 3 minutes. And I think you can do the math, but it definitely is not even close to 1%. Okay, and this is not something which is unrealistic. It is in terms of the percentage. Quite a few will probably find that your numbers are not terribly far from these.